All right. Well, I hope you guys are having a wonderful day. Today, we're going to talk about rational expressions. We're going to be talking about this for the next few weeks. We're going to really hammer this, trying to really understand how to operate on them, how to add them, subtract them, even looking at multiplication and division down the line. And then we're going to use that skill set on how to add them and subtract them and do whatever we got to do to operate on these rational expressions in order to solve our rational equations. Now, to start off with, you might ask yourself, what really is a rational expression? Well, a rational expression is a type of function. It's a function in which we're going to spend a considerable amount of time really looking at, in which it's going to essentially be like a fraction, where we're going to have a numerator and we're going to have a denominator. Now, the numerator and the denominator, they're both going to be polynomials. So up here, we have a polynomial. And down here, we also have another polynomial. So maybe some things such as x over x plus 2. That's going to be a rational function that we'll look at. Now, another one might be something like x squared plus 3x all over x plus 2. That'd be another one. Or even if I was to put a coefficient of 3 in the front or a 5 up there, that would be another type of rational function. All I really need is I need the numerator and the denominator. They both have to be polynomials. Now, what's not a rational function is when I have things such as square root over x plus 1, or if I have something like x squared plus the cube root of x plus 2. Just really anything in which it's not a polynomial. Now, there are echoes of these rational functions that we'll look at, and some of the skill set that we're going to be looking at here today could transfer over when we're looking at these things look like rational functions, but they're not. So this is good skill set here. But what we're really going to be looking at are not these kind of functions today, but these kind of functions right here. So the very first question I got to ask is, whenever we're looking at our rational expressions, well, how would I combine them together? For instance, what if I was to have 1 over x, and I'm going to add it to 1 over x plus 2? How would I actually add these two rational expressions up? Well, the first thing is this. When looking at these rational expressions, they're really echoes of our fractions. And guys, if I look at how to add up fractions, that same skill set that we learned way back when gets transferred over when looking at these rational expressions that we're going to add together. So let's take it back. Let's say if I'm looking at 1 over 3 plus 1 over 5. And the question is, how would I add up my fractions? Well, to add up my fractions, I got to get a common denominator. I got to make my denominators identical. I got to make them the same. But how do I do that? Well, one thing I can do is I can look at the denominator for each one of these pieces and ask myself, what's missing? So I can look for things such as like the greatest common factor and just see what I need on each one of these pieces to make it work. Now, let's take it back a little bit further. When I'm looking at my fractions, what really is a fraction? Well, if I had something like 2 over 6, what this is really telling me is that I'm really asking myself, how many times does 6 go into 2? Now, it's a little hard to see this with this proper fraction, so let's make it improper. Let's say if I had 3 over 6. Excuse me, 6 over 3. I'm going to ask myself, how many times does 3 go into 6? And we'd say it's going to be a value of 2, mainly because if I had 6, 3 divides into it 2 times. See, that's really what a fraction is. A fraction really is this division problem. So when I'm looking at my rational expressions, I'm really asking myself, how do I divide polynomials? In kind of a roundabout way. So when I look at my fractions here, in order to get a common denominator, I note this, that whenever I'm looking at my fractions, like something like 4 over 4, 4 over 4 corresponds to 1. Why? Because just like in an example, when I had 6 over 3, which maybe like equals 2, I would say, how many times does 3 go in 6? You say 2 times. Right here, I would say the same thing. Here I would have my numerator, and I'm going to divide it by my denominator. And 4 goes in the 4 1 time. So as long as my numerator is identical to my denominator, we have 1. And this right here is going to be very, very useful. Because if I come back to the 1 over 3 plus 1 over 5, the way that I would add up my fractions is I do have to get a common denominator. And the way that I do that is this. I take the 1/3 and I multiply it by 1. And I also take the 1 over 5 and I multiply that by 1. And in order to make this match up the way that I need to match up, is I take maybe this one here, and I'm going to convert it. I'm going to recalibrate it. See, I can take that 1, and 1 can be expressed in lots and lots of different forms. One such form is I can take it, and I can say 5 over 5. And likewise over here, I can take the 1, and I can express it as 3 over 3. Now, because I have it as 5 over 5 and 3 over 3, whenever I multiply now this fraction and that fraction, I multiply straight across. So it's numerator times the numerator, the denominator times the denominator. And what I get here is I have 5 over 15. And here I'll have 3 over 15. And if you notice, my denominators, they're identical. They're the same. And as soon as my denominators are the same, what I'm going to do is add and subtract the numerators. Do whatever the operator is telling me to do. Now, the reason why we're doing this goes back to that distribution property. That distribution property is kind of whack-a-mole. It pops up quite a bit in mathematics. But if you go back to that property for a moment that we use when we were factoring, here we have our A, B plus C, we have our AB, and we have our AC. See, what we have is this form, which is that form. And I can take this 5 over 15, and I could recalibrate just for the moment, just so you can see why we have to get a common denominator. This right here and this right here, that's like your A. Right here and right there. So if you're going into the field of teaching, or if you're trying to teach someone about why you need a common denominator, guys, it's right there in the distribution problem. So you can tell your students, well, we got to get a common denominator based upon the distribution property. Now, truthfully, they may not matter too much to them, but at least now you know. Because whenever I take this and I pull it out, 1 over 15, I'm left with my B, and I'm left with my C. In other words, when I'm adding up my fractions, I got to get a common denominator. And as soon as I do, look what I do to the numerators. I add or subtract them. And 5 and 3 will give me 8. Okay, so we know how to add up fractions. So how do I then translate this, transfer this to working with rational expressions? Well, guys, it's the exact same thing. See, whenever you're confronted with a hard problem, what you want to do is not give up. What you want to do is you want to find that echo of truth. See, we go back to the easy problems, the problems that we know how to solve, so that when it comes time to solve the harder problems, we have some kind of sense of direction as to where to go. See here, I'm not sure what to do here, but because I understand how to add up fractions, in which I multiply it by 1, and I take the 1 and I adjust it so it matches up to the piece, the factor that I'm missing, I can understand how to solve this one like that. See, I'll do the exact same thing. I'll take this and multiply it by 1. Then, like we did down here, I want to take this one and recalibrate it, re-express it, so that everything's going to work out the way that I want to work out. So this one, I'm going to take it and I'm going to rewrite it as x plus 2. And for this one, what I want to do is I also want to take that and recalibrate it, but I'm going to write it in terms of x over x. And if you notice, I have a fraction, this rational function, times this one. And to solve those, I multiply the numerator by the numerator and the denominator times the denominator. So up top, what I'm going to have is I'm going to have x plus 2 all over x plus 2. And in the next one, I'll have x all over x plus 2. And the denominators are identical. They're the same. So add and subtract, where the operators tell me to do, the numerators. So here I'll have x plus 2 plus x all over x plus 2. And one thing I want you to take note of, look at my denominator. It's still in factored form, isn't it? I didn't expand out. I left it the way it is. I don't always have to take my polynomials and expand out. That's not something that I always want to do. Sometimes it's a whole lot better, actually, to keep it in factored form. In fact, a good rule of thumb is keep it in factored form for as long as you possibly can. And when you need to, unzip it, distribute, and then maybe collect some like terms if you need to in the problem. So right here, I'm going to leave my denominator the same. But in the numerator, I do see some common terms up top. I see an x and another x. And if I want to add up like terms, I'll have 2x plus 2 all over x plus 2. Now, I could factor out the 2. That's fine. But it's not going to matter much in this given problem. Now, it could say 2x plus 1 all over x plus 2. But there it is. There's my problem. My two rational expressions, when I add them together, that's my answer. Now, I'm just a little bit curious, because I'm just kind of a curious kind of guy. What if for a second, I take x and I set equal to 3? Well, if I set x and equal to 3 and I take it and I drop it in, guys, look what I get. 3. 3 plus 2 is 5. 2. And 3 and 1 is 4. We have 8 over 15. Go back to our problem over here, where we looked at the 1/3 plus the 1 over 5. Our answer was 8 over 15. You think that's a coincidence? No. See, the mechanics, the way that it works when I'm adding up my rational expressions is the exact same way when I'm adding up my fractions. The extra level of complexity of taking the numbers away and turning them to x, that's the only real difference here. but it works exactly the same way. Now, with that said, let's say for a moment, if I take this problem and I slightly adjust it. Or I'm still looking at these rational expressions. I still want to add them and subtract them. But let's say if I'm looking at something like 1 over x plus 1, subtract it off. And let's say 5 over x squared minus 1. And I want to combine these. I want to subtract these. So the question is, how do I subtract these two rational expressions? Well, just like we did over here with the 1/3 and the 1/5, we got to get a common denominator. We do exactly the same thing when I'm looking at it, this right here. Now, what I could do, I could do this. I could just simply say x squared minus 1 over x squared minus 1, and multiply the other one by x plus 1. I could do that, but that's going to make the problem pretty complicated. Especially if I take this, and if I said this was 5x instead of 5, and let's say this was going to be 4 plus x. If I did this, my denominators, yes, they would be the same. I would still get x plus 1, x squared minus 1. But look what I got to do in the numerator now. See, I have x squared minus 1 times 4 plus x. Subtract it off, 5x, x plus 1. And I got to start collecting all my like terms. See, I'm not done with the problem yet. So I still have to do the operation of subtraction here. So what does that mean? What's it tell me that I have to do? I'm going to have to distribute and collect my like terms. See, I'm going to take the x squared and multiply it by 4, and the x squared multiplied by x. But when I do that, can you see what's going to happen? Can you see why this is a little bit more challenging, a little bit more complex going this route? Look what I get. See, when I have an x squared times an x, guys, I get a cubic. And then I'm going to have to take this and keep expanding out. I'll have a 4x squared, and then I'll have a minus x minus 4. And then over here, I'll pick up a 5x squared. Now, be mindful of the negative sign. The negative also gets distributed in. So it'd be incorrect for me to say 5x. Add 5x. It's really a negative 5. So I make sure it's a negative. And then once again, it's all over x plus 1, x squared minus 1. But I got to clean this up. I would have an x cubed. And here's my square terms. 4x squared minus 5x squared. That does get me an x squared. And I got this one. Minus x, minus 5x, minus 6x, and then minus 4. All over x plus 1, x squared minus 1. Now, here's the deal. It's not simplified yet. How do you simplify it? How do you factor a cubic? Well, we're not quite there yet on how to factor a cubic. We'll get there eventually later in the term. But how do I do this? Do you see the difficulty here? So when I'm trying to add and subtract my rational expressions, I don't always want to haphazardly jump right into it and just say, take the denominator here and put it over here, and take the denominator here and put it over here. Yes, it works, but look how hard you're making the problem. And the question is, do you want to work a problem the hard way or the easy way? Choice is yours. Now, for me, I'd rather work a problem the easy way. I don't really like working problems the hard, complicated way. So here's what I'm going to do instead. Go back to the drawing board. It is a drawing board, and that's your bad joke for the day. I'll think of maybe another one for tomorrow. Maybe. But I do want to come back to this. And what I want to do is I want to get the denominators the same. And how I get them the same doesn't really matter so much, as long as I don't violate any rules in mathematics. And one of the things that I do see here in this problem is this: the x squared minus 1. Now, think back. We talked about this when we're looking at our special factors. Do you remember what this is called? Well, see if you can put it together. What am I doing to this term? Am I cubing it? Or am I squaring it? And look what's happening here. I'm taking not a product, not a sum. I'm taking a difference. So do you think it might be something like a difference of squares I have? See, by acknowledging and seeing this pattern of the difference of squares, guys, I can speed through this pretty quickly by knowing the structure. And remember the identity. When I have a difference of squares, when I have a squared minus b squared, I can take it and I can factor it as a minus b and a plus b. That's what I want to do. See, what I want to do is I want to unlock the denominator. I want to know the secrets of the denominator. I want to know exactly what it's trying to tell me. So I'll have my 4 plus x, x plus 1. And when I factor the denominator, oh, look at this. X plus 1, x minus 1. Guys, look here. I already have an x plus 1 in both of these rational expressions. So if I want to get a common denominator, what do I really need? Well, what I really need over here is I need to multiply by 1. And the way they want to write the 1 is x minus 1 over x minus 1. Now, when I multiply through, my denominators are the same. I will get x plus 1, x minus 1. And notice how I'm keeping the denominators factored. I'm not expanding out. It's a waste of time. Don't worry about it. Keep it in factored form for as long as you possibly can. Up top, I will have my x minus 1 and my 4 plus x. But it's no longer 5x times x plus 1. It's just 5x. So whenever I distribute now and start collecting my like terms, notice the complexity of the problem has been drastically reduced. When I just expand out, I'll have 4x, and then I'll have an x squared. Then I would have a minus 4, and then a minus x. Start collecting all my like terms, and what I'll have here have an x squared. I have a 4x. I have a minus x, giving me 3 of them. But then I'm going to subtract off 5 of them, minus 2x, minus 4. Now, the next thing is I do want to consider the possibility that maybe I can factor this further. So I just want to kind of analyze it real fast, see if I can actually factor this quadratic. So once again, there's a 1 from the x squared, and I can look at the constant term and just see, okay, so -4, the factors consist of 1 and -4, or -1 and 4, or 2 and -2. But do any of these factors sum up to be a value of -2? No. So we're considering that as a prime polynomial. We can't factor it anymore. Now, go back and reflect. The way that we were doing it earlier was complicated. It was hard. Yes, we can rush right into it. Yes, we can multiply the denominators by it. But when it comes time to do the simplification process, can you do it? See, if you simplify as you go through the problem, it's getting baked into the process as you go through it. So when it comes time at the very end to start simplifying, you're already taking care of so much of it. Guys, I'd rather work a problem the easy way than the hard way. And the easy way is to pause, stop, reflect, ask yourself, is there something that I can do to the denominators so I can see what's actually missing, the piece that I actually really need to make this problem work? Let's try another one. Go ahead and take the expression x over x plus 2 minus 3 over x minus 2 plus x plus 1 over x squared minus 4. Go ahead and take a moment and see what you get here solving this problem. Let me give you a moment here to think about it. Okay, so when I'm trying to solve this problem, what I want to do is that, once again, I want to inspect all the denominators and ask myself, what do they look like? Is there any commonalities between them that I can really jump on, that I can really use in my simplification process as I'm adding them up? Because once again, guys, what I could do is I can say, I can multiply this by x plus 2 and x minus 2. But do you see the problem that's going to come about from there? I get a degree 4 polynomial in the denominator. Ouch. And look at the numerator. If I multiply this by x plus 2 and x minus 2 in the numerator denominator, that's going to be quadratic times the linear. And it doesn't go down the linear. All it's going to do is take that power and crank it up. See, you're making the problem more challenging if you do that. So what I want to do is pause, stop, analyze it a little bit closer. And one thing that I do see here is, once again, I see this difference of squares identity coming in full display. So I want to take the x squared minus 4, and the first thing I want to do is I just want to recalibrate. And by doing this, oh, I see exactly what I need. For this rational expression, what I really need is an x minus 2. For this one, what I need is an x plus 2. Now, I look at each one of these pieces individually. So if it's causing too much concern doing 3 pieces all at once, just cover the other ones up. Work at making this piece first. So here I'll have x. And then here, whenever I see a negative, I do want to be a little bit cautious that I'll make any kind of distribution error. So for this piece, I would have something like -3 x plus 2. In other words, guys, use parentheses. They're free. They're good. Use them. And here, this x plus 1. And notice how the denominators are all the same for all these pieces. So I could write out for all 3 of them again, or simply just note that it's this. Now, the next thing is we need to expand and start collecting all of our like terms, because I still have to do the operator of subtraction and addition. So this piece will get me an x squared minus 2x, and let me put it over here. And here, once again, just note when you're distributing, the negative goes along with it. So I would have 3x, and if I was to say 6 or plus 6, that's incorrect. The negative goes along with it. See, it's -3 times 2. So that's going to be a -6. Here, x plus 1. All over x minus 2, x plus 2. And notice by making strategic choices for my denominators on how I need to multiply my rational expression, the simplification process has been baked into the problem. So there might be a little bit of simplification I have to do at the end. Guys, I don't have to do a whole lot. X squared, there's no other x squareds up here. I do have a minus 2x and a 3x, so minus 5x, plus 1 more gives me a minus 4. And then a minus 5. -6 and 1. Okay, now, the next part of the puzzle is I just got to make sure that there's nothing else that's going to reduce down, no other issues of that regard. So I do want to factor the numerator just to double check. So once again, I do have -5. Look at the factors of it. And I see that I'm going to have -4 gets me from a -5 and a 1. Let's check it. So x times x is x squared. X times 1 is 1x. So you have x squared plus x. -5 times x is -5x. And a -5 times a 1 is a -5. Did I get back to where I need to get to? Absolutely. Now, on the exam, just make sure you're listening to the set of instructions. If the instructions tell you to keep things in factor form, make sure you keep things in factor form. If it wants you to expand out, make sure you expand out. But either one of these two answers, they're both valid in the very end. They're both correct. Issue might just be on formatting. But notice how there's nothing else that divides out. So our rational function has been completely simplified. Okay, so double check and see if you got the exact same thing. Well, what I want you to do is I want you to work through these 4 problems. And I'd like for you to add and subtract them, whatever you have to do in the given scenario. You're going to take these problems and you're going to upload them later on so I can see what you're doing, so I can make sure that you're understanding the concepts. If you're having difficulty still and you're still not for sure how to solve these kind of problems, guys, set some time around this week. Schedule a time with me and let's sit down and let me make sure that you're really understanding these concepts. See, I want to make sure you're understanding these concepts so that you can keep making progress in your education, so you can keep moving forward. Okay. Well, if you need anything, stop on by. Other than that, you guys have a great day.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.